Hi there! I hope that you're all doing very well and are excited about today's class. I know I am. I am your personal physics teacher and a lifelong learner of physics, Rima McMullen, and my mission is to bring physics and math to everybody sitting at their home, to make education accessible to you all, to make everybody believe that they are capable of understanding and learning math and physics. And indeed, we can all do it. These lectures are my first step in the direction of accomplishment of my mission. In today's lecture, we are going to solve introductory problems of error analysis. And as always, you can find a PDF link that contains the problem statements for all the problems that we are going to solve in today's class. And there will be timestamps posted for all the problems, so feel free to jump to whichever problem you're interested in. And like always, I would once again recommend that before you watch me solve problem, please try it on your own. And sometimes you have to struggle. Sometimes you will struggle, and only then you will be able to solve the problem. But do not give up. Let's begin our class. Here's our problem number 1. Let's read it together. In an experiment consisting of 5 trials, to measure the time period of a simple pendulum, the following measurements are recorded. Here are our measurements. So do not worry if you do not know yet what time period means or what a simple pendulum means. I promise you do not need to know those things to solve this problem. Let's see what the problem asks us to do. It says, calculate the mean absolute error, the fractional relative error, and the fractional percent error in the time period. So what we are going to do is we are going to make a list of what is given to us, and we are going to make a list of what we are asked to do. And then we are going to see how we go from what's given to us to where we want to reach. Which kind of formulae, which kind of equations relate those two things. We're going to find a path between what's given to what we want to solve for. Alright, let's write down the values of these time periods. Let's tabulate them. We're given time period, call it as T1, T2, T3. Okay. Let's scoot this a bit up so I can fit this all on the screen. I have a tendency to write larger than most people do. .34 seconds, T4 is 20.20 seconds, and T5 is again 20.20 seconds. So this is all that we are given. We are asked to calculate. Alright, we'll calculate mean absolute error. What will be the mean absolute error? Mean absolute error. How do we represent the symbol for it? It will be mean. So there's a bar over it. Absolute error. The bar, the line over delta t, that means the mean or the average. And this delta t, it is the absolute value of the error. What it means exactly, we'll see that in a minute. What else are we asked to solve for? Fractional error. The fractional error, also called as, let's use a different color. Relative error is given as the mean absolute error divided by the mean value of the time period. And the fractional percent error in the time period. The fractional percent error is often called as just percent error. And that is going to be the relative error, which is this over here, times 100. So hopefully you remember these things from the previous chapters in this playlist where we have talked about these things in great detail. If you have not watched those videos, if you do not yet know what mean absolute error is, what relative error or the fractional error, percentage error, these things are, I strongly recommend that you watch those videos first. Although I'm going to show everything that you need to know to solve these problems here, but it will make more sense if you have watched those previous video lectures. Alrighty, back to this. Our first goal is to calculate mean absolute error, delta t bar. Now this mean absolute error, let's call this as A. Okay, we used yellow color for that, so we're going to stick with yellow color because color matters. Delta t bar. How is this defined? This is defined as absolute value of t bar, which is the average of all of these time periods, minus ti. What is this ti? Ti can be 1, which is t1 here. I could be 2, that means t2. I could be 3, 4, or 5. And then we are going to sum all these values of absolute errors and divided it by 5. Anyway, so this is the formula for delta t bar, mean absolute error. So you see that to solve for mean absolute error, what do we need to know? T bar. So let's go ahead and solve for t bar. To solve for t bar, what do you need to do? You need to sum up all of these values of times. So this is going to be ti, where I goes from 1 to 5, divided by 5. Have we seen these kind of notations before? All it means is that T1, this sigma here, this is a Greek symbol. It's a capital letter sigma in Greek. It means summation. It means sum over. So what we are doing here is this I here, I'm writing as Ti. I is a variable. I will run from 1 to 5 here. So I'm summing this Ti. What it means is that Ti is equal to T1 plus now I is equal to 2. Next I is equal to 3. Then it is equal to 4. Next it is equal to 5. Divide all that by 5. So the numerator here is this numerator. It is just a short form to write this entire sum of 5 terms. Now 5 terms are not too much to write. But what if I had 100 terms or maybe 5,000 terms? Then do you think it will be very convenient to write T1 plus T2 plus T3 plus T4 blah 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 till you get to maybe 5,000 or 10,000, however many number of T's we have. In that case, it's very convenient to write this notation of summation. 20.23 plus 20.19 plus 20.34 plus 20.20 plus 20.20. Divide this by what? 5. So what is the sum of all these numbers? This gives me 101.16. All right. 101.16 divided by 5. What do I get? 20.232 seconds. So here's our average value of the time period. Now, following the rules of significant figures, this answer should have how many decimal places? This should have only 2 digits after the decimal, following the rules of significant figures for addition. However, since we are going to use this value in another calculation, which is the calculation for mean absolute error. The rule says keep all of these digits after the decimal, and at the end, when you have the final value for this delta t bar, round it off to the correct number of decimal places or significant figures based on whatever the rules might be. Okay, so now I know t bar. I have to solve for delta t bar, which we said was equal to summation t bar minus ti, summation I goes from 1 to 5, divide this by what? 5. Okay. Now, I do realize that you may not have seen equations written in this notation before. So what I will do is, I will first write this down. I will write it out explicitly, symbolically, and then plug in the numbers. That is, then we will write down the equation numerically. What I mean by that? Let's see. So I'm going to write or expand this equation symbolically now. What I'm going to do is this t bar minus ti. I goes from 1 to 5, so i's first value is 1, t1. Then we have these lines here, which means the absolute value. Then we have the summation here, plus. Next value, t bar minus I is going to be 2 now, plus t bar minus t3, plus, let's scoot it up, t bar minus t4, plus t bar minus t5. Okay, here we go. Now it fits. Divided by. We'll divide this by what? 5. Next, we are going to now plug in the values. t bar is equal to 20.232. So 20.232, there's a decimal here, minus t1. t1 is 20.23 plus t bar 20.232 minus t2 here 20.19. All right, here, plus 20.232 minus t3. What is t3 equal to? 20.34. Plus, now i's value will be 4. 20.232 minus t4. 20.20 plus 20.232 minus 20.20 absolute value. Alright, let's bring this equal sign down here, and then we are going to now plug in a line over here. Why? Using the automatic shapes, because my drawing sucks. I can't draw. Divided by 5. Okay. So first one is 20.232 minus 20.23. What does it give you? 0.002. So that was this one here. And then I have 20.232 minus 20.19. What does this give us? Third one. The third term, it gives us 0.108 plus this fourth one. This is going to give us 0.032. And the last one is going to give us exactly the same thing again, 0.032. All of this will be divided by what? 5. Let's add up these numbers and see what we get. When we add all these numbers at the top, it gives us 0.216 seconds divided by 5. When we divide 0.216 by 5, what do we get? 0.0432 seconds. So this is our mean absolute error in the time period. 0.0432 seconds. Okay. Now, here's the thing. It will be to the same number of decimal places as are the individual time periods. So all the time periods, they were till 2 places after the decimal. So the final answer for the mean absolute error, it should round off to 2 decimal places. So the answer should be 0.04 seconds. Alright, so this was our part A, delta T bar, mean absolute error in the time period. What are we going to solve for next? Next, we're going to solve for fractional error. What did we say? The fractional error, also called as the fractional error, which is also called as relative error. This is defined as mean absolute error divided by the mean value. Now here once again, we are going to keep delta T bar and T bar to the same number of decimal places, to the same number of digits for which we have solved them before we are going to round them off. Why? Because if we use these rounded off values, then we are going to end up either overestimating or underestimating the fractional error. But if we keep the exact number of digits as are in the calculated answer without truncating it, without rounding it off, then we are going to get the correct value of the error. Make sense? Okay, I hope it does. Let me know in the comments if it doesn't. 0.0432 and the average value of time period, we solved it over here, 20.232. What are the units? Seconds at the top, seconds at the bottom. Seconds cancels out. What do we get? We need the assistance of calculator to make this fast. We get 0.002135231. Very small number. I'm going to write this as 0 because it really is 0.002, which is basically 0. Next, we are going to find the percentage error or relative or fractional. Percent error, which is equal to fractional error or the relative error times 100. So that is going to be delta T bar divided by T bar times 100. I'm going to use this value 0.0021 times 100. What does this give me? 0.21%. So this is the value of the percentage error. So this was our problem number 1. I know it looks longer than it really needs to. It's basically arithmetic. There's not much physics in here. There are some rules and there's just some basic mathematics that you have been doing since, let's say, 4th grade, I presume. Okay, you should be, if not. Moving on to problem number 2. Problem number 2 is basically a twin of problem number 1. So I highly recommend that you try this problem on your own first and then come to watch my solution. In any case, Let's see how it is solved. So the problem says 5 readings obtained in an experiment are here. We're not even given any units for these, but that doesn't matter. These could be length, these could be time, these numbers could be force, momentum, pressure, whatever. It doesn't matter. It would not change the solution. Okay. Let's see what we're asked to solve for. Calculate the mean absolute error, just like what we did in the previous problem. Fractional or relative error and the fractional percent error in the quantity being measured. We're not told what quantity it is, and nor do we need to know that. We're going to solve this problem exactly the same way as we did the previous problem. First thing we're going to do is tabulate this data. So let's go ahead and tabulate the data. Let's call these values as x. So we're going to write down the value of x1, x2, x3, x4, and x5. Let's write it here on the side. 100.2 What are we asked to solve for first? Mean absolute error in x. So mean absolute error. In what quantity? In x. So that's going to be mean absolute error. If you want to be very, very precise, you should write these bars around delta x as well. That implies that it is absolute value. That's what the 2 bars mean. It means the modulus, the absolute value. And the bar, the line over delta x, that means mean. So just like we did in the previous problem, we're going to write down the formula for delta x bar, the mean absolute error in x, in its compact form first. And that is going to be summation I goes from 1 to 5. Why? Because we have 5 values of x. Absolute error between, or absolute difference between x bar, the mean value of x, minus xi. This summation is going to be divided by what? 5. So, just like we did in the previous problem, we first have to solve this x bar. Only then we can solve for delta x bar. To solve for x bar, we need to sum these 5 values of x's and then divide it by 5. So x bar would be what? Let me use a calculator to find the summation of xi, where I is going from where? 1 through 5, and we're going to divide this by 5. Let's see what we get. 100.2 plus 99.8 plus 98.5 plus 101.7 plus 97.9. Okay, this gives me 498.1 divided by 5. And that gives me 99.62. So this is our x bar. Now using this x bar, we're going to figure out the value of the mean absolute error in x. Let's see how we do that. Let's go ahead and solve for mean absolute error in x. So I'm going to go ahead and expand this notation in its symbolic form. I did this in the previous problem also, and I'm redoing it. Why? Why am I writing this in the expanded form? Because you may not be very familiar with the expansion of these compact forms. So I want you to see these things a few times so your brain can get used to it. Let's go ahead and write it down. We have x bar minus what? x1. Absolute value. plus. The second one is x bar minus what? x2 plus. Our third absolute error will be x bar minus x3. Okay, let's screw it up. Plus. The fourth is x bar minus x4. I'm going to try to write this a bit smaller so I can fit it all here. X bar minus x5 divided by 5. What do we get? X bar's value is, we have it here, hang on, 99.62. Okay, 99.62. What is the value of x1? x1 is 100. Alright, we're using white color here. 100.2 absolute value plus absolute value of 99.62 minus 99.8 plus. Okay, let's scoot this up a little bit. 99.62. You know what? If you think this is going slow, feel free to fast forward it. I can write only so fast, but the technology will let you fast forward. I believe it will let you fast forward only to 2 times though. That should work. 99.62 minus the last one here, 97.9. Now let me check this thing before I go on to solve this. 99.62, all in pink. Then x1 100.2, x2 99.8, x3 98.5, x4 is 101.7, x5 is 97.9. Good. Now I'm showing to you as I'm doing it that I'm checking my work. Why? Because if I get one number wrong here, my answer will be wrong. And if you're solving this problem on a multiple choice test, then you're going to be in some big trouble if you write even one number wrong. So it's a good habit, it's a good practice to check your work as you go. That's why I'm showing you my whole process of how I would do it. And that is one reason why it takes longer to solve it. Make sense? I mean, if I were to just solve it real quick, I would keep doing it and you may or may not understand everything. Let's go ahead and draw this line here. And then we're going to write what? 5 at the bottom. And it drives me nuts to have this equal sign there because it's supposed to be next to this line over here. So here we moved it. Okay, cool. What are we doing next? Now we need these values here. So 99.62 minus 100.2. You know that it's going to be a negative number. But since we are taking the modulus, since we are taking the absolute value, it's going to give us a positive answer. Let's see what it would be. So now to solve this, we're going to pretend that there are zeros here. The last digit in the x's will need to pretend like it's a 0. Now if you see, 99.62 is 0.38 away from 100, while 100.20 is 0.20 away. So 0.38 plus 0.20 is 0.58. So first will be 0.58. And the next one, 99.62 minus 99.80 is again a negative number. But since we are taking the modulus of it, it will be a positive answer. So what is this going to give us? To go from 99.62 to 99.80, I have to travel 0.18 units. So it is 0.18. Next, 99.62 minus 98.50. Okay. So 98.50 to 99 is 0.50 units. And then I have to go another 0.62. So 0.50 plus 0.62 will give me 1.12. Fourth one, 99.62 minus 101.70. Again, it's a negative number, but since we're taking absolute value, it gives us a positive answer. So 99.62 is 0.38 units away from what? 100. So 0.38 to go from 99.62 to 100, and then 1.70 to go from 100 to 101.70. So this is basically here 0.38 plus 1.70. Then we have this last one. This is going to be, alright, 97.90. You add 0.10 to it. You get to 98. 98 plus 1.62 will take you to 99.62. So plus 1.62. If you're not allowed to use calculator, then what I just showed to you might be a useful technique. Now we gotta add all these big numbers. We can do it. Look how. 0.18, 1.12. Okay. This will give me 1.30. So here's my 1.30. Then 0.38, okay, another color. 0.38 plus 1.62 gives me 2.00. Alrighty. Then let's use yellow. 1.70 plus 0.10. 1.80. Last. 0.58. White color. Line. Beautiful. Divided by 5. What do we have now? Okay. 1.30 plus 1.80. This will give me 3.10. Okay. 3.10 plus 2.00 plus 0.58. Okay. Divided by 5. Alrighty. So 3.10 plus 2.00 is 5.10 plus 0.58 divided by 5. This gives me, now it's easy, 5.68 divided by 5. And this is going to be equal to 1.1.36. So what we have done here is we have solved for what? We solved for mean absolute value of x, 1.136. This is our answer. What are we going to solve for next? Fractional error, also known as relative error. Alright, let's do it. Let's do it. Relative, also called as fractional. So this relative is not your uncle, aunt, cousin, grandpa, grandma. This relative means relative to something, with respect to something. And fractional we know what fractional means. It's a fraction of two things. So, I know. You know these things already. Relative fractional error in x. It will be defined as mean absolute error divided by the mean value. And we just calculated the mean absolute error to be 1.136. And I am keeping this entire value, all the digits, even though at the end I'm going to round this off. I'll show you how when I get there. Divided by x bar, and x bar was 99.62. All right, let's go ahead and divide this by 99.62. We're going to get 0.01140333. That is our answer. So this can be rounded off to what? 0.011. So I'm keeping here what? Two sig figs. If the first digit in fractional error is 1 or 2, then you should keep 2 sig figs. If it is 3 or larger, then 1 sig fig is sufficient. Alright, now once this is calculated, then the next thing is super easy, which is relative percentage error, which is equal to RE is for relative error times 100. And we said the relative error is what? 0.011 times 100. This will give me 1.1%. Now, relative error and fractional error, what are their units or their dimensions? None. They do not have any units, therefore their dimension this. Here in this problem, it happens so that we're not given any units for x. X is just assumed to be a dimensionless, unitless quantity. But had it had any units, then when we divide delta x bar with x bar, then the units of delta x bar would cancel out the units of x bar, leaving the relative error with no units. And if relative error has no units, then the relative percentage error, which is just the relative error times 100, will obviously have no units. So here, this was problem number 2. Like I said, this is basically a twin problem of problem number 1. Look at this. Isn't this beautiful? I think the colors are looking gorgeous here. I don't know, kind of things that excite me. Equations, colors, books, problems, math, science, anything that's, where I get to learn something. Problem number 3. It's going to be different. It's a relatively simple problem, but an important problem nonetheless. Let's look at what problem number 3 says. Problem number 3. 3 objects have their mass labeled on them as supplied by their manufacturer as M1, its value is given, M2, its value is given, and M3, its value is given. Find the combined mass of all 3 objects in their proper form, that is, along with their error. So, error. As you know that error is this number, which is written after plus minus. So these 3 values are the errors. Let's go ahead and write down the values of, tabulate the values of M1, M2, and M3, and then find out the combined masses. So we're told that M1, its value is 92.08 plus minus 0.02. So it is 92.08 plus minus 0.02 what? Grams. M2 is 42.132 plus minus 0.001 grams. And last but not the least is M3. M3 is 79.5 plus minus 0.5 grams. Now, what does it mean? It means that the minimum value of M1 would be 92.06 grams. This is the least possible value for M1. M1 cannot be any smaller than this. And the largest possible value for M1 is going to be when this plus sign is being used. So 92.08 plus 0.02 gives us 92.10 grams. This is the maximum, the highest possible value for M1. M1 cannot be greater than 92.10. It can be equal to that. And likewise, at the lower end, M1 cannot be smaller than 92.06. It can be equal to that, but not smaller than that. Same way, the smallest possible value for M2 is when you take this minus sign here and find out what is 42.132 minus 0.001. That is equal to 42.131 grams. And to find out the highest possible value for M2, we'll use this plus sign. What would that give us? 42.132 plus 0.001 gives us 42.133 grams. For M3, the minimum possible value for M3 will be 79.5 minus 0.5. What does that give us? That will give us 79.0 grams. And the highest possible value for M3 is when you take this plus sign. That will give you 80.0 grams. Do you agree with me so far? You do? Yep. Okay. So now to find the combined value of these three masses. What is the least possible value for the combined mass? The least possible value will be when you add what? When you add these three together, right? So M combined, this is M total minimum. What is that equal to? 92.06, 42.131, 79.0, all in grams. Let's add these up. So you can see that they're not all up to the same number of decimal places. The top one is to 2 decimal places, middle one to 3 decimal places, and the bottom one to just 1 decimal place. Now to add these up, we're going to pretend like they're all up to 3 decimal places. And let's see what this summation gives us. We get 1, 9, 1, okay. 9 plus 4 is 13. And then I get 10, 9 plus 1 is 10, 10 plus 4 is 14, 14 plus 7 is 21. Here. So this is the MT is total M minimum value. Okay. Now let's go ahead and find out M's highest possible value. So M T max will be 92.10, 42.133, and last is 80.0. We're adding these up. Here we go. To find the maximum value of the combined mass, we're going to do what? We're going to add these three values over here. Let's see what do we get. We get here 3, 3, 2, 4. 8 plus 4 is 12. 12 plus 9 is 21. Alright. Now, to get the uncertainty in M, we're going to, this M total's uncertainty will be the range of the MT max minus min divided by 2. So let's go ahead and find this range now. That range will be 214.233 minus 213.191. This gives us 2. 13 minus 9 is 4. 0. 1. 1.042. 1.042 divided by 2 gives us 0.521 grams. So this is our combined masses error. To find the combined mass, you're going to add these values of M. 92.08 grams plus 42.132 grams. Okay, I don't need to write grams yet. Plus last is 79.5 grams. What does this give us? We add these three numbers and we get 213.712 grams. Now we're going to have to follow the rule of significant figures, which says when we add or subtract some numbers, the final answer should have as many decimal places, as many digits after the decimal, as the number with the least number of decimal places that is being added or subtracted. And that in this case is 79.5. It has only one digit after the decimal. Therefore, the final answer must have how many digits after the decimal? Only one. So the answer is 213.7. But we are asked to write down the answer in its proper form. That means we need to write 213.7 plus minus the uncertainty, which is 0.521. Now this uncertainty must have the same number of digits after the decimal as the answer does. So it will be 0.5 grams. This is your answer. This was quite a long way to do it. So here what we did was we were given value for M1, M2, M3 in their proper forms. We found the minimum value possible for each of the masses and the maximum value possible for each of the masses. And then we added the minimum values and the maximum values and found their difference, which was the range over here, right? And then we divided that range by 2 to get the uncertainty or the error in the mass. And then what we did, these values of m's, we added them to get the final value of m. And the final value of m, we rounded it off to appropriate number of the decimal places plus minus the uncertainty. Is there an easier way to do it? Yes. We did not have to do all this so much elaborate work. We could have done it in a very, very easy and a simple way. Let's see how. So what I'm going to do is, I'm going to say that M1 is equal to M1 bar plus minus delta M1 bar. So we're told that these values of masses, these are provided to us by the manufacturer. When manufacturer makes something, typically they will make multiple measurements of the same thing and then take the average of those multiple measurements. So for example, these were some scales given to us, the masses given to us. And it is labeled as, maybe it's a dumbbell. And the dumbbell's value is, I don't know, 92.08 grams. So how does the manufacturer know that it's exactly 92.08? It's going to make several measurements of the same dumbbell and then take the average of those measurements. So M1 is the average of those measurements, and the mean absolute error in those measurements is this here. That's one way to look at it. So this is given to us to be equal to what? 92.08 plus minus what? I forget. 0.02. Likewise, M2. Symbolically, I'm going to write this as M2 bar plus minus delta M2 bar. And its value is, let me look it up, 42.132, okay, 42.132 plus minus 0.001. Okay, if you want, you can write these parentheses here. Even if we do not write the parentheses, here it is understood that the grams, it's really going with both of these numbers here. All right, M3, the last one, equals M3 bar plus minus delta M3 bar. And I believe it was 79.5 plus minus 0.5. What do you think? Yes, I was right. It feels so good to be right, doesn't it? Okay, so we're asked to find the combined mass. There's a rule. When you're adding or subtracting some numbers that have errors with them, then you would do with the numbers addition or subtraction, whatever you're asked to do with these numbers here. But these errors will always add whenever you're adding or subtracting. So here, the total mass will be equal to M1 bar plus M2 bar plus M3 bar. Error plus minus delta M1 bar plus delta M2 bar plus delta M3 bar. Now this is already calculated. We have already done this. Where? Right over here. 213.712. Let's write this down. 213.712 plus minus delta M1. Let me use a different color here. This was equal to what? 0.02 plus delta M2 was 0.001 and the last delta M3 was 0.5. And these are all in grams. What do I get? 213.7. This has to be rounded off to one digit after the decimal. Why? Because when you look at these numbers over here, the 79.5 has only one digit after the decimal, so the sum of these three must be rounded off to one decimal place. That is the rule of significant figures for addition and subtraction. Okay, plus minus. What does this give us? 0.521 grams. Next rule of significant figure says that the uncertainty must be up to the same number of decimal places, same number of digits after the decimal as the number that the error or the uncertainty belongs to, which is this number. So that means your answer is 213.7 plus minus 0.5 grams. So this is a much easier way to solve the problem than to find the minimum of every mass and the maximum and add up the minimums together and the maximums together. Take the difference of the two, which is the range, divide that by 2 to get the uncertainty or the error. It is a completely 100% valid, legitimate way to do it, doing that long way. That's the way to understand it. This is the way to do it after you have understood it. Alright, so this was your problem number 3. Let's move on to problem number 4 next. Problem number 4 is kind of a twin problem of problem number 3. So we have learned the easy way of doing it now, and that's how we're going to solve this problem. Let's see what we are given in this problem. We're told that 5 lengths measured in an experiment are P, Q, R, S, and T. Okay, calculate the value of the following expressions here. These are the two expressions. Find their values. So you can see that we're adding and or subtracting these lengths. So let's go ahead and tabulate these lengths and go from there. Alright, so first one is P. Let's write this P as P bar, the average value of P, plus minus delta P bar. And what is it given to be? 10 plus minus 1 centimeters. That's our first one. Second is Q. What is Q given to be? Q is given to be, let's call it as Q bar plus minus delta Q bar is equal to 19.2 plus minus 0.02 centimeters. Then we have R. R, we're going to write this as R bar plus minus delta R bar, and its value is 20.20 plus minus 0.05 what? Centimeters. What do we have next? We have S. Let's write S as what? S is equal to S bar plus minus delta S bar, and that is 8.932 plus minus 0.002 centimeters. And last but not least, we have T. What is T equal to? T is T bar plus minus delta T bar 101.83 plus minus 0.01 centimeters. Okay. What are we doing next? We are asked to solve for P plus Q plus R. Okay. So we are basically adding these three. So P plus Q plus R. What does that give us? A, P plus Q plus R. Solve for this. This is going to be equal to what? Add P bar plus Q bar plus R bar. Plus minus delta P bar plus delta Q bar plus delta R bar. Are you with me so far? P bar. What is P bar equal to? 10. Okay. 10. Q bar. What is Q bar equal to? 19.2. Okay. 19.2. R bar. 22.20. Plus minus delta P bar is 1. Okay, 1 plus delta Q bar 0.2, 0.2 plus delta R bar 0.05. And of course, these are all in centimeters. Okay, we get, here's what I'm going to do. I'm going to line these up. 20.20, 19.2, 10, 0, 0, 0, 0, 4, 9 plus 2 is 11, and here we go, 51.40, which will be rounded to 51. Why? Because this 10 is a whole number. Therefore, the final answer has to be a whole number. Now, while adding the uncertainties, what do we get? 1.25. So our answer is for P plus Q plus R, 51 plus minus 1.25 centimeters. Now since this 51 is a whole number, the uncertainty must be a whole number as well. That means our answer will be 51 plus minus 1 centimeter for P plus Q plus R. Now that you know how to solve for P plus Q plus R, can you solve for T minus S plus R on your own? Let's see. Here, let's see. T minus S plus R. This will be equal to T bar minus S bar plus R bar. Plus minus delta T bar plus delta S bar, not minus. Uncertainties will always add. The errors always add up. All right. T bar. What is T bar equal to? T bar is 101.83. Then we have a minus S bar, 8.932 plus R bar, 22.20 plus minus delta T bar 0.01 plus delta S bar 0.002 plus delta R bar 0.05. Okay. What do we get for the first one? Let's see. 100, let's clear it. 101.83 minus 8.932 plus 22.20 is 115.098 plus minus sum of these three. That is going to be 0.062 centimeters. Now the question is, this final answer, it will round off to how many decimal places? 2. Both of these, T and R, have 2 digits after the decimal. So this will have to be rounded off here, like this. So this will give us 115.10 plus minus. This will also go to 2 decimal places now. 0.06 centimeter. What is this? This is our part B. T minus S plus R. So this was our problem number 4. Let's move on to problem number 5 next. Problem number 5. It says, calculate the relative error in the measurement of 2 lengths. So we are given these 2 lengths. We're asked to calculate the relative error in L1 and L2. So what is L1 equal to? L1 is, let's call this as L1 bar plus minus delta L1 bar is 1.02 plus minus 0.01 meters. The relative error in L1 will be equal to delta L1 bar, which is this, divided by L1 bar. That's it. So this will give us 0.01 from here meters divided by 1.02 meters. Now here, as long as it is written correctly, and I hate to say it, I have seen some other resources that I'm not going to name, where I have noticed that the number of decimal places for uncertainty and this number are not the same as they should be. And if it is written correctly, where the number of decimal places are same for the uncertainty as is in the number that the uncertainty belongs to, then when you find this relative error, the number at the top, which is the error, and the number at the bottom, the measurement, they will have same number of digits after what? After the decimal. So that means when you get rid of the decimal, what happens is this. You could just write down the number at the top divided by the number at the bottom. In other words, all I have done is here, multiply this by 100. 0.01 times 100 is 1 and divided by 100. So 1.02 times 100 is 102. And multiplying and dividing by 100 is like multiplying by 1, which changes nothing. So here's your relative error, 1 divided by 102. I'm not about to calculate it any further than this. If you want, you're welcome to do it. The answer will be, it will be less than, I don't know, 0.1 over 100. So 102 is almost 100. 1 divided by 100 is what? 0.01. So the answer will be smaller than even this. So it will be more like 0.009 or 8, something like that. Whatever. Now I'm curious. Now I have to check it. Because otherwise I wouldn't be able to sleep. And what time is it? 1:18 a.m. It's about time to sleep. And okay, this is awesome. I was absolutely right. My guess was not such a random guess after all. Okay, next we're going to figure out the relative error in what? L2. Go ahead and do it yourself and see what you get. What I will do is I'll put the answer in the PDF document that's going to be linked in the description. You'll find the answer there. I'm not going to solve it. Please do it yourself. Let's move on to problem number 6. That is going to be different from this problem and all the previous problems that we have been doing. Problem number 6. A physical quantity, y, depends on 3 other physical quantities as shown by the equation shown below. Okay, so these 3 other physical quantities seems like they are A, B, and C. What is the percentage error in the measurement of y, which is this, if the relative errors in the measurement of A, B, and C are 2%, 1%, and 4% respectively? Now, in this case, y is equal to what? A squared times B5 divided by square root of C cubed, which can be written as C to the power 3/2. So now here you will see that A, B, and C, these are being multiplied or divided with each other. Well, division is same as multiplication. Division is multiplication by the inverse. So there's no difference between division and multiplication, just like subtraction and addition are basically the same processes or operations. How? Well, subtraction is addition of the negative, right? Okay, so for addition, we saw that the uncertainties or the errors add, and so do for subtraction. However, for multiplication and division, the rule is different. For multiplication and division, here we have relative errors add. What I mean to say is that the relative error of the final answer, that equals the sum of the relative errors of all of the parameters or the quantities that are being added or subtracted. But not just that. The power here, these powers, they play a role. How? This is how. So the relative error in y is delta y over y. That is going to be relative error in A, delta A over A, but this power of A becomes the coefficient of this relative error. Same way, this B to the power 5 becomes the coefficient times the relative error in B, plus, now even though this C, when it comes upstairs, its power becomes negative 3/2. But when the power goes over here as the coefficient of the relative error in C, this power, it comes as a positive coefficient, not a negative coefficient. Okay, so what we are given are the relative errors, percentage errors. These are relative percentage errors in A, B, and C are 2%, 1%, and 4%. And we are asked to solve for percentage error in the measurement of y. So that means if I multiply this equation here by what? 100. Then I get delta y over y times 100 equals 2 delta A over A times 100 plus 5 delta B over B times 100 plus 3/2 delta C over C times 100. Now I'm given that the percentage error in A, percentage error in B, and percentage error in C. These are what? 2, 1, and 4% respectively. So this is 2, this is 4, and this, sorry, I miswrote. This is 1, and the last one is 4. Okay. Times these coefficients here, 2, then we have this plus, then after plus I have this 5 times 1 plus this 3.5 times 4. So these numbers in yellow, these are the percentage errors. 2 is percentage error in A, which is this expression inside the yellow parentheses in the first term. 1% is just the percentage error in B. 4% is the percentage error in C. And we're asked to solve for percentage error in Y. So let's see, what do we get? 2 times 2 is 4. 5 times 1 is 5 plus 2 goes into 4 2 times, and 2 times 3 is 6. This gives us 15%. So the percentage error in Y is equal to 15%. That's what we were asked to solve for, and here we have done it. So see, it was such a small problem. It was a very simple problem. Let's look at problem number 7 next. What does that say? Here's our problem number 7. It says an experiment involving the measurement of physical quantities A, B, C, and D with percentage errors of 2%, 4%, 6%, and 8% respectively. What is the maximum percentage error in the calculation of P? Where P equals, here, I have written this down as A to the power 1/2, B to the power 1/2 divided by C squared times D. So I know that the percentage error in P equals, here, the power of A 1/2 times percentage error in A plus this power of B comes down as coefficient times the percentage error in B. Okay. Plus I have this power of C 2 times percentage error in C last. We have this D, D's power is 1, plus 1 times, we don't need to write 1, percentage error in D. And what are we given? Percentage error in A is what? 2% times this 1/2 plus percentage error in B is 4%. So this 1/2 times 4% plus this 2 over here times percentage error in C is 6%. Okay, it's not fitting. And last is percentage error in D is 8%. So what does this give us? This gives us 2 goes into 2 ones. This is 1% from here. 2 goes into 4 2 times plus 2% plus 2 times 6 is 12% plus 8%. This gives us 23%. This is the percentage error of P. As you can see, these problems are quite straightforward problems. There's not really much to do once you know what needs to be done. Alright, let's look at next and the last problem for this lecture. Problem number 8. Calculate the following quantities for a sphere whose radius is measured to be equal to 35 centimeters with a percentage error of 5%. Okay, so for this sphere, the radius is 35 centimeters plus minus 5% error. So what is 5% of 35? How do you find that? That's going to be 35 times 5 over 100. What does that give us? That gives us 35 times 5 divided by 100 is 1.75. So this is 35 plus minus 1.75 centimeters. And I know I have been beating this drum that the uncertainty must be up to the same number of decimal places as is the number. So technically speaking, this should be 35 plus minus 2 centimeters, because now this is a whole number just like the actual radius is. But since we might, just saying we might, use this uncertainty here to do some calculations, so we want to keep it as 1.75 for now. So the first part says uncertainty or error in the measurement of radius delta r. Already found it. 1.75 rounded off to 2 centimeters. So that's our first answer, 1.75 centimeters rounded off to 2 centimeters. Next is percentage error in the volume of the sphere. Okay. percentage error in V. It will be given as delta V over V times 100. Alright. Now, to solve for the percentage error in the volume of a sphere, let's begin with the formula for the volume of a sphere, which is 4 over 3 pi r cubed. Using the formula that we just learned in the previous two problems, what we're going to do is we're going to write down the relative error in volume V, which is delta V over V equal to, on the right hand side, 4, pi, and 3. These are three constants, and there's no uncertainty in the constants. So on the right hand side, we'll get 3 times delta R over R. We already know the value of delta R to be 1.75 and R is 35. Now to get the percentage error in volume, let's multiply this by 100. What does this give us? On the left hand side, percentage error in the volume equals, on the right hand side we get 3 times 1.75 times 100 divided by 35. What does this give us? This gives us, let's see, 1.75 times 3 times 100 divided by 35. And that is 15% error in the volume. What else are we asked to solve for? Uncertainty or error in the calculation of the volume, delta V. Okay, so now we know V is solved for 15%. Next we want to solve for the uncertainty or error in the calculation of the volume V. Okay, so we know that delta V over V times 100 equals what? 15. Alright. We're going to solve for what now? Delta V. Very well. Delta V will be equal to 15 divided by 100 times V. You get this much math? This gives us 0.15 times V is 4 over 3 pi r cubed. 0.15 times 4 over 3 pi. What is r equal to? 35 cubed, and this is cubic centimeters. What does this give us? This gives us is a huge number. This is equal to 26939.157 cubic centimeters. Big number. But what is V? V is 4 over 3 pi r cubed. This is going to be equal to 179,594.38 cubic centimeters. So yeah, sure. I mean, it's a huge error. But the volume, it's even huger. Is huger word? I don't think so. But it sounded cool, so why not? Alright, so we have solved a total of 8 problems for this class today. Next class, we're going to solve some more problems. They are relatively shorter problems. They're going to take less time as compared to this lecture. Maybe as less or as little as 50 to 60% of the time that we invested on this lecture. You're trying to learn physics. You're trying to do some science. It is going to take time. You cannot rush through these things. I keep being told that my lectures are too long, and these days kids do not have the patience to watch this long lectures. I'm sorry to break it to you. If you're not willing to put your time into the subject, then subject is not going to reward you. Then you're not going to understand it the way you would like to understand it, the way that will make you feel comfortable, the way that will make you feel happy about it. And when you really understand something, when you really get something, the kind of satisfaction it gives you, it's totally worth the time. I promise you. You will see it if you put your time into it, put your effort into it, solve these problems. All right. I'll see you guys next time. Until then, keep studying, keep working, keep learning, keep exploring. That's the only way to live life. See you next time. Until then, have a good one.